Hello and welcome to this episode of 15 Minutes Hikka. I am Amal Medhi from Thiruvananthapuram. Today I am going to talk about a topic that will deal with some of the curious ways in which quantum particles behave. So here's the overview of my talk. You might have gone through the talks by Professor P.K. Soria before. In his talks, Professor P.K.S. gave a beautiful overview of what is classical physics, what is quantum physics, etc. For example, he mentioned that classical particles are particles as we human perceive in our day-to-day experience. For example, a cricket ball. Though strictly speaking, in physics, by particle we mean point particle, but anyway. So for such a particle, we can talk of position and momentum at the same time. For example, for a cricket ball, we can talk of the ball hitting the ground at a certain spot with a certain momentum at a certain time. Also, classical mechanics is deterministic. It means that if we know the force acting on the particle and the initial conditions, then we can predict how exactly the particle will move in time. Professor P.K.S. also mentioned that quantum particles behave in strange ways. In fact, their behavior is beyond our normal human perception. For example, the position and the momentum of a quantum particle cannot be precisely determined at the same time. Quantum particles show both wave and particle-like characters, and the motion of quantum particle is probabilistic. So in this talk, what I plan to do is to give a little bit more, discuss a little bit more into the details of what exactly these things mean. So I will bring up situations which will illustrate how the quantum particles are different from classical particles. I will also give some ideas about the preliminary aspects, ideas about the formal aspects of the subject of quantum physics, and I'll apply this formalism to a few simple quantum mechanics problems which will further illustrate the motion of quantum particles. So I hope that the talk will be very useful to the science students, especially the physics students, who will feel more curious to know deeper into the subjects. At the same time, I also believe that the general audience will be able to appreciate the subjects and will wonder about the ways of the microscopic world. So with these preliminaries out of the way, I come straight into a series of thought experiments by Feynman, who was one of the greatest physicists in the last century. So these experiments are called thought experiments because Feynman didn't really perform those experiments, but it's the results of the experiments can be predicted from the already existing knowledge of physics. So here's the first experiment with bullets. So in this experiment, there is a gun that shoots bullet randomly in all directions and uniformly. There's a screen in front of the bullet with two holes, and there's a backstop here and detector which can move up and down, which can detect the bullets. So if we do the experiment with one of the hole closed, then and you spray the bullets here, so some of the bullets will go straight to the hole and hit at this point. Some of the bullets may also get hit the edge here and get deflected and then move here and here or here. So it will be distributed according to a certain distribution. So the detector can it will count the bullets, and we can find out what is the distribution of what is the probability that the bullet will hit a certain point at a distance x from the center of the screen. Okay. So if we do the experiment, we'll find that the probability P1 when the hole 1 is open, the probability that the bullet will hit a point, it will be given by a curve like this. So you can see that the probability is maximum at a point like this, that is along that line here, and it decreases as we go either side of this point there. Okay, so this is very intuitive. Yeah. because most of the bullets will come straight here, and some of the bullets will get deflected from the edges and it will move both up and down. So instead, if we repeat the experiment with hole 1 closed but with hole 2 open, now this time we'll see a probability distributions like this is shown here. Now if we keep both the holes open, then for a given point there's a probability that the bullet can come through either hole 1 or hole 2, and so the net probability that you will find a bullet at a point now is the sum of these two curves, and so it will look like this. Now the maximum is at the center, because at the center there's a probability that the bullet can come from both this hole and that hole, and these two basically probabilities get added here. So we get this thing, and it looks pretty intuitive, so you can easily understood the shape of this curve here. Now let's say we perform the experiment with waves. Again, classical waves, classical object. So there's a source here which creates ripple through water, let's say, and there's a circular wave spreads through and it hits the screen. So here I'm keeping this hole closed here, so this wave will hit this hole here and create secondary wave, which will again spread like this circular wave, and it will hit the detector. So here at this point straight across the hole, in this case the detector measures the intensity which is square modulus of the wave amplitude. The intensity will be maximum at this point, and it will die down as you go away from this point. So again you see a distribution like this, which was the same shape as for bullet. Now we repeat the experiment with hole 1 closed, hole 2 open, and this time you get the wave will pass through this hole and it will hit here, and the intensity distribution will look like this curve that has been shown here. Okay. Now if we open both the holes, something very interesting happened here in this case. So we open both the holes, these two secondary waves that come out of these two holes. Okay, they meet, they superimpose each other at here, and so as a result, the intensity pattern that is produced in the screen, now it looks like this. That's the intensity now. Okay, now you can see that this intensity is not simply the sum of the intensity I1 and I2. So it's a definite pattern here, and this intensity is in fact is proportional to again the square of the amplitude of the sum of the individual two amplitude. Okay, and so this pattern is called interference pattern. So here I have taken a video from YouTube that shows the interference of water wave, basically simulates animation. So just watch this video.
Waves. When a wave passes through a hole, it spreads out on the other side. If there are two holes, two waves are produced. When you have two waves, they interact with one another. In some areas, they strengthen each other, and in other areas, they cancel each other out. This creates a striped pattern. This is the exact same pattern that we saw before. This means that all objects really behave like waves.
Okay, so that's basically wave which produces when two waves meet, so they produces interference pattern. Okay, so now I want so you already might know about the mathematical details of waves, but here I'll quickly refresh you about the basics of the mathematical description of wave. So here let's take a simple case of a sinusoidal, one-dimensional sinusoidal wave that moving in plus x direction like this. The question is how do we describe such a wave mathematically? Okay, so we do that by defining a function y of y that gives the displacement of a point of a particle in the wave, okay, at a point x and at time t. So such a function is shown here, which is a cosine function. Okay, you can also use a sine function. It has the same, it gives the same wave basically. So it is a constant and the cos of this function, the 2 pi by lambda into x minus omega t. So if we picture this function at a given instant of time, let's say t equal to 0, if I plot this y displacement as a function of x, it will look like this. So the distance between two peaks is the wavelength lambda, and this maximum displacement is called amplitude, and the omega is called angular frequency. Okay, so this is the snapshot of a wave. This is described by this equation like this. If you allow this wave to move in time, then it looks like this wave that's propagating along x direction. Okay, that's the wave. Now we know that the sound is wave, and some sounds we hear are loud, some sounds feeble. Light is also a wave, and some light we see are bright, some not so bright. So what is this thing that we are perceiving here by our ears and eyes? So that's the intensity. Okay, and mathematically intensity I is proportional to the square of the wave amplitude A. Okay, so if the amplitude is higher, the intensity will be more. So now if we combine two waves, if we superpose two waves, what happens? So let's say there are two waves, that is y1 and y2, which are identical. Everything is same amplitude, they have same wave number k, same frequency omega, but the two waves differ by a certain phase angle. They don't exactly match. There's a lag between these two waves. Okay, if the two waves are propagated to the same medium, okay, a particle in the medium will be disturbed by both the waves, and so the resultant displacement will be simply sum of these two displacements. So if you add these two functions, so you'll get the expression like this, which is another wave, because it has the same form basically, same wave number, same frequency. But its amplitude is modified now. The amplitude is now given by A cos phi by 2. So depending on this lag between these two waves, or depending on the phase difference, the amplitude will be different. So it can be it can be 0, or it can be more than the individual amplitude, right? So in this particular case, so if we I think the phi was equal to 60 degree, then if we add these two waves, so the amplitude, we get a resultant wave whose amplitude is higher than the two component waves. And so intensity is also will be given by this the same expression, okay, square of the amplitude. So what is complex is simple means, so we can also represent a wave in terms in terms of a complex function. So if people who are not people who who has not seen complex number, so this complex number is I should not say that, probably all of you have seen this. So the complex number is written as a plus ib, where a and b are two real numbers, and I, which is square root of -1, is called imaginary number. Okay, so we can represent a wave by using a complex function, by keeping in mind that it is the real wave is actually given by the real part of the wave function. So I can reuse the complex expression where this constant a, which is the amplitude of the wave now in this form, also includes the phase of the wave. Okay, So what is simple here? What is the simplicity here? The simplicity here is when we need to add two or more waves, it is much easy if we use this complex notation. Okay, for example, if we have two waves with different amplitude, we can simply add it like this. So this is resultant here. This is resultant amplitude, and so we can calculate the net intensity easily. So that's the mod of A square, and A is A1 plus A2, and we get an expression like this. So you can see that the intensity is the sum of individual intensities plus this extra term that depends on the phase difference. So this is the extra terms that produces the modulations in intensity or the interference pattern. Okay. So if this phase difference is 2 and pi, is an event multiple of pi, then this cos of this quantity will be 0. I will get a maximum intensity. If the phase difference is odd multiple of pi, then this cos of that angle will be -1. So the intensity will be minimum. Okay, so but here I should point out that when it comes to classical wave, using complex wave function is optional. Okay, but you will see that for quantum particles, in fact, using complex wave function will be an essential. So this already gives you an idea that quantum particles are something really different. Okay, now let's come back to the Feynman's experiment again, but this time done with electrons. Okay. So here's an electron gun that shoots electron randomly in all directions, and is detector which detects the electron. And in this experiment, it is always found that the detector, when it receives an electron, it always receives the whole of an electron. It doesn't receive a fraction of an electron anywhere. Okay, when electrons comes here, it always comes in one single lump. Okay. So here again we ask the question, what is the probability that an electron arrives at a distance x from the center of the screen? Okay. So let's say again we keep the hole 2 closed, keep hole 1 open, and we shoot the electrons and we detect it, and the probability distributions in this case would turn out to be a curve like this, which is again same as seen before for the waves or the bullets. Okay. So probability looks as before for bullets. Now if we do the other way around, keep hole 1 closed, keep hole 2 open, now the probability curve will look like this, again same as before. Okay. Now is the surprise. Now we open both the holes. Now electrons can come through either of these hole, and here is the net probability that we will see. Okay, it's very strange here. For bullets, we saw that the net probability was simply sum of P1 and P1 and P2, but in this case you can see that instead the curve here is a modulated curve, just like the interference pattern that was found for the water waves. Okay, so now how does this happen? It's very strange here, because the electrons are a priori they are not waves, and so how can they interfere? I mean, water, they produce interference because the same water wave got split into two different from the two holes, the secondary waves, and they came and they meet at a point and they produce the interference. But for but for electrons, how can that happen? How so? Because because the detector always receives one full electron, so electron doesn't get split. So how does it come through? I mean, does it come through only a single slit at a time, or can the electron comes both the whole somehow? So it's very strange here. How does this happen? Okay. So then this experiment cannot be described by conventional wisdom. So then it turns out that we are forced to associate a certain wave character to electrons. Okay, otherwise we cannot describe the results of such experiment. Okay, and so we do it. So we associate. We say that there's a complex function called psi xt, which is associated with an electron. Okay, but what this wave function signify? So we interpret the mod of psi square, the square mod of psi, as the probability that the particle will be found at that position x and at that position x and at time t. Okay, if we measure this position, and the wave function psi itself is called the probability amplitude. So we can see that though in this case the psi, the wave function itself here is more fundamental, but it is not measurable. Okay, it is beyond our experiential and experimental apparatus. The only quantity that we measure, that is we can possibly we can taste or smell, touch, hear or see, is the square of its modulus, its probability. Okay. So now you can ask this question, then how does this electron look like? Does it look like a wave like this? The answer is we don't know, because we can't really see an electron. Okay. However, if we can probe an electron in different ways, various ways, and you will find that it will behave in ways that will correspond to a picture like this. I mean, not for the electron, but for the wave associated with the electron. So we have run out of time today. So let us summarize what we have done so far. So we found that the experiment with bullets gave us results that we expected for classical particles. We found that waves show the phenomenon of interference, and we also found that electrons also strangely showed wave-like interference effect, and it was necessary to introduce the idea of wave function for electrons. So in the next talk, what we are going to do is we are going to take up the electron experiment again and try to probe the electrons a little bit more to understand how exactly it produced the interference pattern. This will lead us to the realization of a fundamental limitation about the process in which we can probe microscopic particles, and we'll be forced to abandon classical mechanics, and so we'll formulate a new theory of quantum mechanics, and we'll apply it to some example problems to see what this new mechanics describes. Okay, so I stop here today, and I thank you all for your attention. See you next time.